Hello. It's fuller. This presentation. Yeah. The first. Both are the presentations for this session, so we can take both of them because. Yeah, yeah, exactly. Yes, sure.
Sorry, your Ramos, right?
Sorry?
Rui Ramos?
Paula.
No. Yes, sorry.
Yes. Paula.
Paula Amaral.
Paula Amaral, yes. You can say it in Italian.
Yes.
Paola, no? If you say in Italian.
Yeah,
Paula.
yeah. Paula. Hello, can you hear us? Hello, can you hear us? Sorry, you are the share?
Yes.
Okay. So I'll say that we can probably start.
Okay.
Is everything okay?
Yes.
Okay.
So, we have the both presentations. We have one presentation. Right? Okay, nice. And then how to switch to another presentation?
The third one can help you.
Okay, you are here.
Yes, I will be here during the
Okay,
presentation.
nice.
The first one and the second one will be in presence.
Yeah,
The fourth one.
Okay.
But the third one will be remote.
Okay.
Let's do it. I will be over here.
The chef is here.
Yes.
You are the chef?
Yes.
Okay. Good morning. Technical assistant. Okay. And she's the audience. And the speaker.
Also
Virtually.
virtual.
They are virtual. Está tudo ligado?
Já liguei tudo já.
Já está? Okay. Start.
Okay.
Open the windows, please, and let's try to have a fresh.
Yeah,
Thank you.
6 consegues ver? Não, já está a ver.
Olha, Miguel, olha, boa. Isto tem que estar sempre no máximo, que é para estar ligado.
Tá bem.
Não? Está bem?
Está bem.
Apesar de dizer 20 e tal, é o mínimo.
Deixa bem aqui. Agora cá e depois deixa o share dar. No ecrã. Isto é ecrã. Deixa que isso deixa não. Pronto.
Eu não estava a ver como é que se saltava de uma para a outra, mas isso é que pode chegar para aí.
Windows Shift. Já veio.
Alguém por aí já?
Está no grupo do WhatsApp dos voluntários.
Estou a mandar esta agora.
Já.
Obrigado.
Mas eu não vou chegar a carregado.
Good morning, everybody. I'm pleased to start this session for the dynamic sessions common, as you know, computational methods in advanced networks, computational methods in advanced networking technologies. I'm Mustafa Sharif Sadi, assistant professor of University of Trento. From the Department of Industrial Engineering. So I will let's start. We are a bit delayed, but we can cover it. We start with the first presentation of title a fractional epidemic model for multi-malware attacks in wireless sensor networks by professors Leila Muradi and Islam Farsimana that are the organizers of this session as well. So I ask Islam Farsimana to present interesting
Slides. We have a pointer.
So you can do it from here, yeah?
Yes,
Maybe I can sit there.
Yeah, it's easier.
Yeah, it's okay.
Because I guess that we have not a pointer or something like
There's
that.
no problem.
Okay. Okay.
Perfect.
Everything is okay. Okay, hello everyone. Thank you for coming. I'm Islam Farsimana, and I'm a researcher from the University of Salerno, Italy, and I'm here to present our work related to a fractional epidemic model for multi-malware attacks in wireless sensor networks. That has been done by other colleagues, also Leila Moradi, Marcello Trovati, and Professor Francesco Palmieri. We are all from University of Salerno, except Professor Trovati from University of Lancashire, UK. Okay, let's start with the motivation of the work and the problem. The wireless sensor networks, known as WSNs, have a lot of applications in the real world in the improvement of IoT environment, but also they have a lot of problems related to limited, for example, limited sources, and also about defensive mechanisms and so on. And one of the threats related to this kind of networks is malware propagation, which is more critical because it can affect the network in several ways. Malware spreading in a scale-free network, same as biological epidemic models, same as, for example, SEAL, SEAS, or SAIL, and other biological models. So it can be inspired. It can be inspired from this kind of disease to model malware propagation in this kind of networks and also other networks. Most existing WSM models for malware propagation are based on ordinary differential equation or ODEs, that they are memoryless. I mean, for example, it's kind of Markov chains. There is no memory related to the states that have been occurred before. So the goal of this work is a more realistic multi-malware propagation model for WSM that can incorporate memory effects during the propagation period. The starting point of this kind of propagation, I mean, the integer order of the model that we have improved related to malware propagation is S, E1, E2, IR, multi-malware models of this researcher, with two exposed classes for two simultaneous malware types. This one, E1 and E2, because we have in this model, we have 5 states, 2 for exposed nodes, infected, recovered, and susceptible nodes. We generalized the ordinary and the ordinary model using fractional differential equation with Caputo derivatives of order alpha between 0 and 1. And our goal, as I said before, is to capture the effect of, the memory effects. Our contributions are formulated a fractional order for this model with the dimensional consistency and derive equilibria points, free equilibria and endemic equilibria points. The basic reproduction number are 0, which is so important in this kind of to investigate this kind of propagation and prove local and global stability, and validate numerically using FABM, to simulate the situation using MATLAB and study the effect of varying alpha between this between 0 and 1 and maybe more and less. There are a lot of work that have been done related to this kind of propagation models. For example, I don't know here this work and other works, and most of them are based on ordinary differential equations, but the states are different. For example, here we denotes vaccinated, for example. Some other quarantined and other kind of state that we can insert in the model. But the important part of the story is how we can solve the model, that we can have the effects of the memory effects. The gap that we found during studying this state of the art is real multi-malware fractional work does not analyze the effect of varying the fractional order alpha, nor the influence of the main parameters. The sensitivity related to the parameters. Which is, here we can see the transition diagram, for example, from susceptible to exposed to infected to recovered. And all the parameters here, same as, I don't know, for example, omega and other type of parameters that we will control, and we will see how they affect the whole system during the propagation phenomenon. We have 5 node classes. S for susceptible, E1, E2, 2 types of exposed classes, because we are we are studying multi-malware propagation, so we can use this kind of states for two type of malware. For example, two type of malware we can use worm or viruses for these two types, and infectious or infected, and because it's normal to use infectious or infected, and recovered modes. The ordinary system of ordinary equations, ordinary differential equations, that is based on these five equations, and this kind of parameters that we explain here. This is the ordinary type of the system that we want to improve it to fractional one, because we want to also we want to insert the memory effect in the system. Here is the type of the derivative we want to use, because you have a lot of type of derivatives that we can use for fractional systems, which is named Caputo derivative of order alpha greater than n minus 1 and less than n, to as I said, to investigate memory and hereditary effects of the model. Also, well suited to anomalous diffusion, non-local attractions, and fractal-like behavior. And the most important contribution of this work is how we can insert the effects of the effects of memory to the system, because it's related to each other. For example, when malware propagates in the system, it's important what happened before to investigate what will happen in future, what will be happened in the future. This is the system that we derive from the normal one, the ordinary one, based on the Caputo derivative, based on alpha. Here, alpha is between 0 and 1, and it can be extended to other type of fractional differential equation. For example, if we have alpha 2.5, we can use 2 as a normal derivative and use 0.5 here. It will be between 0 and 1. So it can be extended to any type of alpha here. And the integer part will be solved same as before. The most important part of the story is here. That I said here, et alpha is Caputo derivative injects the memory and historical characteristics, and every rate parameter is raised to the power alpha to keep both sides dimensionally consistent, and integer order model recovered as if we put alpha equal to 1, it will be the normal model as a ordinary differential equation with an integer, alpha. The most important part of the story is how we can find the solution, and is this solution unique or not. With this theorem, we have proved the existence and also the uniqueness of the solution of the system. So the system has a solution, and this solution is unique. And the second theorem is related to positivity of the solution. And in this region this region is positively invariant. Populations stay non-negative. If in this region the solution will be positive, so we have proved the positivity of the solution. As I said in the first page of the presentation, we investigate 3 types of points. The first one is malware-free equilibrium point, which is heat 0, which is this point. And basically, the production number via the next generation matrix. This is the model that we extract this R0 from the model, and R0 expected secondary infections from one affected node, the threshold from an outbreak. I mean, this is the threshold that we can control, and also we can investigate how the propagation process is going on. If R0 is less than 1, malware dies out. I mean, the system will be free of malware. But if R0 is greater than 1, malware persists in the system and will stay in the system. This is the ending point. When R0 is more than 1, an endemic equilibrium point E star exists. This is the point, this is the situation that infection persists in the system. But these 2 points are some kind of characteristics that we can see here. For example, about local stability, global stability related to R0. As we can see here, for free equilibrium point, which is free of malware, there R0, the basically production number should be less and equal to 1. But related to endemic equilibrium point, which is the point that malware persists, the R0 should be, I mean, when R0 is greater than 1, the malware will persist in the system and will continue the propagation phenomenon. Here we investigate 2 cases. One case is for R0 less than 1, another case for R0 greater than 1, with this kind of parameters which are involved in the system. And also for example, R0 equal to 1, because this is the threshold. So we put R0 equal 1 as a threshold, and we investigate R0 less than 1 and R0 greater than 1. Here we can see when R0 is less than 1, for example, if alpha equal to 1, which is kind of, for example, ordinary differential equation, and alpha equal to 0.8 as a, for example, example of our model, both types are something similar. We can see here, and they will go to be stable in the future, because all something like descending all the charts. I mean, for example, based on the time, the number of susceptible nodes will be decreased, also exposed and exposed to, and also infected during the time, and recovered. Recovered went up, and after that will go down, because first, when the nodes are infected, after the type of the number of recovered should be increased to recover this kind of infected node, and after that, when there is no malware in the system, the number of recovered will be decreased. And here is related to the situation that R0 is greater than 1. I mean, the situation that malware persists in the system. There is no stable point in this, as we can see in this figure. All are something, non-balanced, and they are going sometimes increase, sometimes to go down, sometimes to go up. So this is a situation which is not stable, and the malware will persist in the system. And because R0 is greater than 1, So we can control the system by controlled parameters and derive R0 less than 1. When R0 is less than 1, we can control the propagation phenomena in the system, in the whole system. Here we can see how the susceptible and infected and also recovered nodes behave during the malware propagation when R0 is less than 1 and alpha is the derivative order. As alpha goes to 1, malware leaves the WSN faster because R0 is less than 1. So it's kind of convergence point here, here, and here. Okay. Key findings of this work is the R0 equal to 1 threshold cleanly separate these two parts, R0 less than 1, from persistence R0 greater than 1 proven and simulated. And we investigate the stability of holes at both equilibrium locally and globally across a range of alpha. The fractional order alpha acts as an extra design control lever. It reshapes the convergence speed without changing the threshold structure. Fractional order dynamic gives a closer memory aware description than the integer. This is the point of using fractional order in this kind of systems. And conclusion, as I said before, a fractional model SE1, E2, IR model for multi-malware propagation is the in WSNs with full equilibrium points for endemic and free. R0 and stability analysis were investigated in this study, and this kind of simulations confirm that the theory is is proven, and the fractional model outperforms the integer order one because the fractional order, the fractional model insert also the effects of the memory in the system. For future work, we can use, for example, we can investigate parameter sensitivity and control strategies that we want to use it. We want to investigate it, and data-driven calibration on real WSN traces, because we use simulation. Maybe with this kind of data, we can have kind of real-world investigation. So thank you for your attention, and I'm here to
Interesting presentation. Any question?
I have one question. This is not my field, so maybe my question is my questions. But from your presentation, I really didn't understand what was the importance in practical terms of the memory.
Yeah. Yeah.
What is why it is so important to have a model that has?
Because, for example, when we have memory effects in the system, we can investigate what happened before, based on the behavior of the malware, because it's kind of propagation model. The behavior is so important. How did they behave during this propagation? If we want to, if we don't have the memory effects, we don't have any, anything to know about the history of the propagation. And anytime we investigate, same as the first point of this study. But when we have the memory effects and the history of the propagation, we can control the system based on the memory effects and based on the history of the propagation. That's why it's important. That's why I mean, that's why the fractional model outperforms the integer model, because it's kind of it includes also integer model if we choose alpha as 1. So it's important to have the history of the model to control the future of the model. That's why we use this fractional type of the differential equation to solve the model. It was not easy to prove the existence and uniqueness of the solutions, but it works.
I have another question. Thank you for your interesting presentation. Do you think is it possible to apply this idea, extend this idea, for example, for another type of the differential equations, such as, for example, parallel equations? What do you think about that?
There are a lot of types of differential equations that we can use. I mean, most famous one is integer, fractional, partial, and this kind of systems. Yeah, it can be it can be extended to this kind of differential equations. But we should see, okay, this extension will solve another problem related to this system or not. But I think it will be nice to investigate also based on, for example, that I'm thinking about partial differential equation. So it's important, for example, to control the model based on a lot of parameters, partially, not global. Yeah.
Thank you so much.
Welcome, thank you.
Now we invite Professor Paula Amaral to present a set of interesting work with the title of Annual Detection and Root Case Analysis, how Retainability Contextual Anomalies in Radio Access Networks.
First of all, thank you for the organizers of this session. And the work I'm going to present has a very broad theme. I am from the Department of Mathematics, and David with my master students on the master on decision and data science, and is doing his master in collaboration with Multivision, and João and Rui are from Multivision. And Multivision is a consulting company in telecommunications and information technology. So we have mathematicians, decision science people, João is more on the side of machine learning, and Rui is an electronic engineer. So you see a very very broad team. So I will, in this presentation, give a brief introduction, speak a little bit about the background for the work that we applied, to understand the methodology that was used, and then present some results before the conclusions. So we all use radio access networks when we use our computers, when we use our mobile phones. And these antennas that are called cells are distributed geographically. And every time that we are making, for instance, a call, we connect to one of the cells. And then depending if we are moving or not, then this connection is transferred to another cell and so on. Okay? So this is the core network of radio access networks. And the issue here is
can we research, have some full diagnosis? And I was very surprised that I didn't know, because really this is the first time I'm working on these kind of problems, that most of the monitoring of the network is done manually. So there are these guys that have this huge screen where they see several key performance identifiers for the cells and try to understand if there is anomaly. And after identifying there is anomaly, they have to find the root cause analysis. So what is the problem to try to solve it, okay? And this is a very complex system, and it's very time consuming. It's very difficult to scale. So today we have very large networks, and so it's really difficult to do this in real time. And so that was the motivation to find a system that does that automatically. Not only it detects there is an anomaly, but also tries to identify the root cause. Okay? So, as I mentioned, the base to analyze these are these key performance indicators that there are 95 or more related to each cell. And so through these values here, you try to identify if there is some degradation in the network. Okay? So what we wanted to do is to detect this normal network behavior in an automatic way and understand, differentiate it between persistent degradation, and only this persistent degradation requires intervention. And we wanted to understand why these anomalies occur. There can be lots of reasons for a network to start failing or operating with less quality. And if we do that, it will help to support faster operational decisions. Okay? So these are our goals. To detect the anomalies, to distinguish between the persistent, which are the ones that are serious and should require more investigation, from the sporadic ones. And once there is the identification that there is a persistent malfunction of the network, try to explain why it is happened. So this is what we call the root causes, and this is done, of course, to reduce this troubleshooting in mobile network operators. So that's the idea. Okay? So the main contributions is that we are working with the real data, and I will explain a bit later how large is this data set. And so our contributions is a scalable anomaly detection framework, and that we had to first create a seasonal aware detection, identify the root cause using shape explanations, because we have here two different models. We have a supervised model to find the anomaly, this we have, but to find the root cause, it's an unsupervised model, because we don't have historical data with the root causes, and it will take a long time to start keeping this information. At least, they said, at least 3 years to transform this root cause analysis to a system that it's where we can have the data that allow us to do this as a supervised way. Okay, so sharp explanations will help us to understand the contribution of the key performance indicators to the malfunction, and then using this sharp, we know exactly which key performance indicators are more important to explain the anomaly, and then using that, these shape values as an input for a unsupervised model, where we are going to use clustering and to map the shape explanations into a two-dimensional two-dimensional feature space where we can see the relations we use in one. And it's all validated in a real network. Okay? So regarding related work, there are several, of course, papers and contributions to do this. And we have the work of Clinio and all that also use the idea of shape-based supervised clustering. Also, Gomez, Andrade, and al. They use the SOM-based automatic diagnosis. Ferreira had a very nice proposal regarding principal component analysis, and then they also use the feature important approaches. And recently, we have several works which I mentioned, Hassan and Yen, on graph neural networks. Okay? The problem with these approaches is that they have a limited interpretability, scalability issues. So if you have a very large network, this is not going to work. And also, many of these works depend on having these predefined fault labels, meaning treating these as supervised, that I mentioned before. We don't have this level of supervised. Okay? So what are these key indicators associated to each cell that tell us that that help us to know if there is a malfunction or not? Well, there are a lot. There is something like 95 key performance indicators. I just mentioned here a few. The throughput, it is the rate at which data is successfully transmitted. The latency measures the delay during the transmission. The packet loss rate is about the percentage of packets that are not reaching their destiny, meaning that the connection was interrupted. The call drop rate represents the proportion of calls that are terminated. And we will focus on this work on ERAP retainability minus percentage loss. This is a very complicated formula that uses many of these previous key performance indicators. And the reason to, among all the things that we have, to use retainability, for short, I will refer as retainability, to use retainability as the main explanation of our network, as that not only it measures this normal release, but with meaning that lower values is meaning, yes, the network is operating okay, everything is fine. And the way that this key performance indicator is constructed is, it's a really long formula. I don't have time to explain it in detail, but we have the paper, the short paper in this conference. So if you are interested, you can look for it. But it is constructed in such a way that it really reflects the user experience, right? And it takes in consideration things that can affect the hardware, the congestion, because if you are in a concert or a football, in a football game and everybody is using their mobile phone, there is congestion, and so every cell has a certain amount of signals that it can receive and transfer, and so this retainability also enters into information about the congestion or other kind of interference issues. So it is really what were used. And the thing that people do is to look at this retainability, and when it's larger than 2%, then this for them is the indication that there is a malfunction. Okay? So the issue here is that it really requires to analyze this. We cannot have such a rule that it's so fixed, so hard, because we should take in consideration what we call the context-aware detection. For instance, a value of retainability can be normal at noon, where you have a lot of traffic in your network, but the same value can be completely abnormal at midnight when the transmission and the amount of information flowing into the network is lower. So it requires some context. Okay? And there are two things that we should distinguish. What is a sporadic anomaly, meaning something that happened but immediately it was resolved, and distinguish this from sporadic to persistence where the issue continues. And this is really the kind of anomalies that require a real intervention. Okay? Otherwise, these ones are immediately resolved, and so although we want to be aware that they exist, we will focus on persistent anomalies. And just reminding you what shared values are. The shared values allow you to get local explanations about your model. It's essential for black box models, for instance, because there, if you use logistic regression, you have the coefficients and you immediately know what is the importance of each feature to the output, to the regression value. But in black box models, we don't know what is the feature level contributions, and so shared values helps to understand what is the importance of each feature in this model. And so our data set consists of real world data from Multivision regarding a region with 11,407 cells, representing 21 days of observations. We divided these 20 days into 15 minutes intervals. This is the granularity that we used. And we use 95 explanatory counters, and this corresponds to over 2 million of key performance indicators observations, just to have an idea of how large is the data set. And this is not the whole whole cell of the whole network considered in Portugal. So this is the pipeline. So we have the data. We're going to do the composition to remove the trend and the seasonality of our series, to have just the residuals that we want to analyze. And this is going to be done just for retainability. So we are going to use machine learning regression to explain retainability using the other counters, explanatory counters. Then from this model, we are going to extract the sharp explanations, and the sharp explanations are going to be the input of our clustering method. But before we do some feature reduction, and then using the clustering, we will try to understand, based on the clusters, what are the causes of the malfunction. So starting with the composition, we use STL decomposition, meaning that our values are going to be decomposed into the trend, the seasonality, and the residuals, and we are, it is the residuals that are going to give us the information about the malfunction, because the seasonality has to do with the days, the periods of the day. As I mentioned before, in the midnight, something that it's normal at noon, it can become abnormal at midnight, because it depends on the whole flow in the network. So what we are really interested in this composition is to analyze the residuals. And so we will say that there is a malfunction when the absolute value of the residuals is greater than some threshold, TA, and we also use the normalized residuals and give a different threshold TR, and we want to work with both of these scores, because they give different information about the measurement of how large these residuals are. And it's important that we keep both scores simultaneously. Okay? So using these residuals as the input for our regression model, we use the gradient boosting models, and we use light GBM, XGBoost, and GetBoost metric, and to measure the performance of these regression models, we use the root mean squared error. So after training our model, and computing the root mean squared error, we are going to use the shape values of this model and use reduced map dimensionality, and then do the clustering as I already mentioned. Okay. So for this, we use in the STL a period of 96, and for TA, which is the threshold after which the absolute value of the residuals is considered abnormal as 0.5, and the threshold for the root mean square error it's of 2, meaning 2 units of standard deviation away from the average is considered to be abnormal. And so just to show you, this is one cell, okay, so one antenna, which we call cell, and here you can see that there are some sporadic anomalies that are immediately corrected, so this is not a concern. Here, in this case, this is a different cell, where you notice here, this is persistence anomaly, because all these points here are considered outside the threshold that says, no, this is an anomalous signal. Okay? So, regarding the models, we used light GBM because it was the best predictor considering the root mean square error. And then it's another thing is that to use the shock values, we should only analyze the data, the points at which the anomaly was successfully explained. And so also, this is generated by the model, this is the true value. And so we have the threshold here, and this threshold is important to say, yes, we have a successfully explained model or point or not, okay? And so if you see here this graph, we have here the percentage of anomalies predicted correctly, and this is the threshold, and we see that with this threshold equal to 1, we get something like almost 81% of the anomalies detected successfully. So after doing that, we use this reduction technique, OMAP, and with 2 components, and we applied DBSCAN, and we found these clusters. Okay, so we have here 10 clusters of the shape values, meaning that in this region the shape values are similar. So there should be a root cause analysis related to this kind of points here that should be identified. So in these clusters, we only want to work on the persistent anomalies. You could argue, but why are we including the sporadic anomalies with the basic anomalies? Because this was the interest of Multivision to keep all the anomalies, because in the future they also want to analyze what happens there. Okay? And so we had these, only of all these 10 clusters, only these 5 clusters were related to persistent anomalies, and then we had to focus on these to try to understand what was the root cause of that anomaly. Okay? And unfortunately, only for the cluster 7, we were able to identify a specific root cause analysis, which is cell automatic downtime event that can be a hardware or a software fault. And so it's possible to identify directly these key performance indicators with this type of anomaly of cause analysis. On these clusters, there were two possible root cause analyses. So we could be the one regarding pressure congestion or transient events. Okay, so we want to have an output that is more or less like what happens to case 7, where you have a cluster and this cluster is directly identified with specific root cause analysis. And so what we did is there's a future work. And this is, I don't know if you have this experience, but when you work with companies, then you start speaking about the problem and the input comes later. So when you believe that you have all the information, then you tell, no, but there is also this that we should consider. And this happens exactly here when they told us recently that sometimes the performance of a cell is influenced by another cell that has no anomaly. It's working fine, but the way it is working influences the cell that is going to create anomaly. And so what we are doing now is really to incorporate as features of one cell the neighborhood cells KPIs. Okay, so this is all. Thank you so much for your attention. And I don't know if you have questions. I think I was a bit out of time. Right?
Any questions?
Excuse me, what kind of supervised role? Yeah?
We use both, supervise and unsupervised. To find anomaly, to say there is anomaly, supervised model.
Okay, but to
Okay.
cluster?
But to say, okay, there is anomaly, why? And this part of the why, which is the root cause analysis, it's unsupervised. That's why we need the clustering.
So it has the benefit of two.
Well, or the curse, the benefit of the curse, because it would be fantastic if also the root cause analysis was done using a supervised model. No, okay, we have this explains this root cause analysis, this explains this root cause analysis, but we don't have that. So we have to find the retainability and how it explains, using these, the shared values of these, explain the feature importance that then later by a clustering, we try to analyze, okay? And this is done by an engineer, okay? Because we don't have the supervised system. So he was looking at cluster 7 and he said, okay, with this, so this is the question. Okay? And we want to construct something like that where you can identify directly clusters with responses. This is what we are still doing.
I would have just a small question. Do you think it's probably anomaly that doesn't have any consequence in the real-time process of the total process?
Yeah. In fact, we could just remove the sporadic and only work with the persistent, okay? But this was a request of motivation. They said, no, let's keep the root cause analysis, also keeping the sporadic anomalies. I don't know what is the technical reason for that.
So it could be some impacts also from.
Also, yes, exactly.
There's a question about the criterion that you choose, so the root means. Do you think that is it like there are different criterions? Going with normalized one or another MSC normal. You think is it change a lot for that for such?
The experience that David performed, it was really not that, the impact was not that high. And so this is quite heavy in terms of the of time because the data is very, very large. So for the anomaly detection, we had like something like 40 minutes, the model training 90 minutes, and this is very fast. Okay, that part is very fast, but this part is very heavy. Okay, and so there is. He found that the root mean square was the one.
The best option to this method.
I know it tests
So to test
another difference, so that the results here are only based on the pipeline very useful.
Thank you so much.
Okay, thank you so much. Thank you.
Thank you, Professor Paula Amaral, for very such interesting presentation. Now we invite third presentation will be presented by Kainat Ibrar. She presented online. The title is when heterogeneous modalities synchronize, mitigating the desynchronization attacks in multimodal online federated learning.
This will be
online.
It says presence here. So can you hear us?
Yes, yes, I can hear you.
Hannah? Can
Yes,
you hear us?
yes, yes, I can hear you.
Yes. Hello?
Hello, can you hear me?
Yes. Now,
Okay.
yes, but testing on computer, just a second. Hello?
Yes, I can hear you, but I don't know if you can hear me back or not.
Hello? You can hear from there.
Hello?
Yes, I think so. Could you hear that? Could she present by laptop? I mean, we have a problem connecting it to the TV. So if it's not a problem,
you
there's no
have
reason.
to first remove that. Stop sharing my presentation.
Okay, maybe it's.
Okay, so first you have to stop sharing that.
Okay.
Okay. You can even close my presentation.
Yes, it is closed.
It is still here. Okay, it starts.
You can see it.
Okay, that's.
Now check again.
Okay. No. Not this one. Não que está no programa daquela saltice que subiu para Are you presenting? Are you already? You are not showing.
Yes, now I have shared my screen. I don't know.
Okay.
Okay.
Good. Now we can see it. Agora é que vai fazer para aqui.
You guys can see?
We are trying to see, but still, yeah, maybe yes. Okay.
But the substance is not.
Could you share again?
Okay.
Okay, yes, that's nice.
Okay.
Okay,
You
so
can
if you,
share now.
you can share now, yeah.
Okay, okay. Thank you. Thank you so much.
Can you go here?
Yes, yes, I can hear.
Okay.
Yes.
Okay. Um, Hello, everybody. Good morning, and first of all, thank you to all the organizers for giving me this opportunity to present my work in front of you guys and to receive the valuable feedback. My name is Kainat Ibrat, and I am a PhD student in University of Salerno from Department of Computer Science. And I'm here to present my work on heterogeneous modalities synchronization, specifically how we can mitigate the desynchronization attacks in multimodal online federated learning. Um, I'll start my presentation with the introduction, then I'll briefly explain problem statement and my proposed attack and defense models, the experimental setup which I used, and then the results I obtained, and then at the end I'll conclude my presentation with the possible future directions which we can adopt in this domain. So first of all, as you all must be already aware of the federated learning, but just a brief background. Recently, we know that this machine learning algorithm has got a lot of attention due to its distributed and privacy preserving nature. In its bottom and how it's work that we have a series of clients, and each client is maintaining its data locally, and instead of sharing the data, it performs the training locally and transfers the model parameters to the central point or entity that performs the aggregation of these model parameters and then transform it into a global model and then send back the global model parameters to the clients. And in this way, they all are engaged in a continuous process of improvement, and the model improves with a series of rounds until it reaches to a point of convergence, and that's how we preserve the data privacy and also achieve the distributed nature of learning. The problem which I am specifically target is a case where each data has data of different type. So basically, we have clients with multimodal data. So in that case, the traditional unimodal federated learning is not of much use, because in that case we assume that each client is having a data of a single type, and it's not exactly the case of in real world scenarios, because in real world scenarios the clients may contain continuous heterogeneous streams of data, for example, sensors, cameras, IoT devices. So, in order to improve decision making while preserving privacy, we have to work on some multimodal data fusion techniques. But when we talk about effective multimodal fusion, it really depends on accurate temporal synchronization across those modalities. So the data must be synchronized among all the modalities, and then we can perform some fusion or synchronization mechanism. So the problem is that in temporal synchronization, we always assume it to be a reliable, and we haven't studied it as a potential attack surface, because in real world online federated learning systems, modalities operate in different at different sampling rates. So they are vulnerable to sensor delays, clock drift, network latencies, timestamp manipulation. So a very small temporal misalignment can actually disrupt multimodal fusion and then can degrade performance. So it is very because it happens sometimes due to natural difference in sampling rates and frequency or operation differences. So it's very difficult to detect that they are some kind of attacks or some natural occurring phenomena because of the sensor clock drifts or network latencies. So here in this work, we are trying to explore a question that can adversaries exploit temporal desynchronization between modalities in order to compromise multimodal online federated learning systems? And if they are manipulating desynchronization, then how can such attacks be effectively detected and mitigated? So my desynchronization attack model is very simple. We are assuming that of all the series of distributed clients, there are some malicious clients that are manipulating the temporal alignment between heterogeneous modalities. So my attack is basically introducing a small temporal shift in one modality, and in order to create some misalignment between different sensor streams. The other sensor clients are operating normally, and they are normal regular benign clients, but some of those are malicious clients and they are intentionally manipulating the timestamps information in order to create a temporal shift, and this results in disrupted multimodal fusion, because then these temporally manipulated or shifted timestamps clients are basically merged with the benign clients, and then they together send their model parameters to the server, and then server performs aggregation, and then it distribute back the model parameters. So the final global model is actually corrupted one, because it contains the multimodal fusion of mistemporally aligned sensor streams. So it results in lower classification of performance, and because they can be pretended as a normal sensor delays, so they are also very difficult to detect. The defense model which I proposed in to mitigate these types of attacks is based on the idea that if the clients are benign or regular one, they should produce their model parameters which they are transmitting to the server. They must have some kind of similarity among them, and these synchronized clients they should produce some inconsistent updates. So our idea is to measure the similarity score at the servers. So those clients that have the higher score of similarity over the continuous series of rounds, they are most trustworthy clients, because they are kind of sending the updates in a consistent pattern. And those clients where this similarity score is kind of manipulated, or their similarity score is a bit lower, they can be, because these kinds, as I explained earlier, these kinds of attacks are very difficult to detect. So we, for not sure, can remove the updates of those clients from the global model completely, because they can be occurring due to some natural sensor delays. But the idea here is to minimize the effect of their updates in the global model. So based on the scores for a series of rounds, we kind of monitor those clients, and we based on some weights, we kind of lower the effect of their parameters in global model aggregation process. So for those clients who have the consistent results in similarity score, we assign a larger weights to those clients, and their model parameters will have a more effect in global model aggregation. And those clients that seem to be have a malicious and kind of suspicious one, we give them the lower weights, and then they try to reduce the influence of their updates in global model parameters, and then we aggregate their weights. But for this happens for us for a certain number of rounds. If the suspicious clowns are in a continuous pattern of occurring, and they are the constant ones, and after a certain number of rounds, then we kind of totally block their weightage in global model aggregation formation. So after a series of n rounds, uh, we kind of completely remove them in the global model aggregation process. So that's how the model aggregation phenomena works, and this uh, process then results in lower attack success rate. And over the series of round, we expect the not completely remove, but we expect the lowering the attack success rate and improving the F1 score as close as to the point where our model consists of all normal or benign clients. So we kind of trying to achieve the accuracy as close as to the normal model. So in this case, we have a better robustness against desynchronization attacks, and we are also kind of taking into the account of the fact that this might be some sensor delay or network latencies delays as well. So for the experimental setup, we I use this multimodal data set. It is a multimodal data set which contains two type of modalities. It is publicly available, and it contains variable and ambient sensors to capture sensorial data along with the visual data. So we have one stream of data that is coming from the sensor, and the other stream of data that is coming from the camera, and we are performing the synchronization of these modalities based on the timestamps available. And then for feature extraction for vision based data, we performed optical flow feature extraction, and also then we downsampled it to 800 image features, but we did not average all those features in order to preserve the temporal accuracy. For sensorial stream, we performed feature extraction where we have some temporal and frequency features across 42 different sensor signals. In order to mimic the setup with some malicious clients, we assume that out of all clients are 10% clients in each round randomly are selected to be malicious one. And we performed our attack in two different configurations, where in one configuration we perform untargeted attack, and we kind of shifted all the samples of a particular selected modality. In other
Thank you.
case,
It's just 2 minutes left in this conclude.
okay. I try to be concise. So in the other category, we have some targeted attacks, and we only selected one particular label, and we shifted its samples to monitor the effect of both configurations. As the temporal shift strength, we try to consider a very small value, because in our data set, variable sensor signals are sampled at approximately 50 hertz. So our sampling interval must be chosen of approximately 20 milliseconds. So temporal offset kind of ranges in approximately 20 to 100 milliseconds for each modality. So the preparations which we applied are which we selected are applied prior to the synchronization function, ensuring that the resultant multimodal window contains temporally consistent information across modalities. The results which we obtain from this setup shows that when we have small temporal shifts, the attack success rate ratio is a bit lower. As we kind of increase the value of the temporal shift strength, the attack success rate increases alongside as well. And as far as the defense mechanism, we can see that it reduces the attack success rate up to 34.1%, and also similarly improves the overall F1 from 79.1 to 84.7%. So this defense remains effective across different attack strengths as well. If we have illustrate the variation of overall F1 with respect to the temporal shift strength from the plot, it is evident that the model performance degrades consistently as the value of K increases. So for temporal shift strength of larger value, there is more degradation in the performance. And the overall result demonstrate that temporal desynchronization constitutes a practical and effective attack vector in this scenario. So even a small temporal shift can also result significant performance degradation. So it really affects the multimodal fusion phenomena in multimodal federated learning. And the future work is our plan is to extend the approach and to test it on more diverse multimodal data sets where we have more modalities to test, and also to implement this model in a real world scenarios where the system is asynchronous, and we kind of take into account in this factor as well that clients may be sending their model parameters updates asynchronously. So this is a very important factor to consider in future directions. And lastly, right now our system is tested with a very short range of malicious clients, only 10%. So in future we have a plan to implement more stronger coordinated attacks and to improve our defense mechanism as well, to tackle those coordinated attacks. So this is all from my side. Thank you so much for your attention and for
Thank
listening.
you, Madam, for your interesting talk. Now, any questions? You should be a bit managed to close the session. So, there is any question? I have a small, very quick curiosity. I was wondering if I saw the metric, CI metric that considered with higher score, lower score. Is there any motivation to consider such a metric?
I'm sorry, can you repeat your question?
Yeah, the CI metric that you considered, that you already presented, that with higher scores and lower scores. Is there any motivation for considering such a metric?
Yes, the motivation was basically work based on the previous work in the literature, because in past not exactly desynchronization attacks have been explored, but there have been some kind of defense mechanisms where they on the base of filtering the benign and malicious clients, they kind of measure the similarity score factor in order to measure the strength of their parameters. So the basic motivation to use this similarity feature is based on those defense mechanisms that have been implemented in the past. But the novel aspect here is that they have not been implemented in kinds of heterogeneous modalities. So they have been implemented in filtering out the model parameters that are of the same modalities. Here we try to work on different modalities. So that's why this is a novel factor in this case.
Okay, thank you so much. We're gonna thank Kaina Tibra for such interesting presentations.
Thank you so much.
So now we invite the next presentation, the last one that we have a bit time. We should manage it a bit faster. So if you could be a bit just manage a bit faster, because we should close the session at 10:40. So we just have around 15 minutes yet. So sensitivity analysis of the multi-malware attack model in various sensitive networks. So we invite the main presenter.
I thought this one was going to be in presence.
Yeah, actually, yes.
In the program it was.
Yes, exactly, yes. But she already wrote us problems that she had. She couldn't have a problem, and
But I think it works better.
Yeah. Sure. Yeah, that's also yes. Yeah, sure. But yeah, she's actually from Utah Salerno. The same supervisor, the same group of Islam and Leila, and they they already informed us for such problem.
She should have been here, but there was a problem, I think, with another conference that she had to participate. So that's why she decided to go there and present this work remotely.
Okay. Sorry, you have only 12 minutes. Do your best.
Because there is kind of redundancy between this work and another work that I presented already. This work should have been presented by Leila Moradi, but because of some kind of problems, I'm here to present this work. The title is Sensitivity Analysis of the Multi-Malware Attacks Model in Wireless Sensor Network. It's close to the work that we have already presented. So I will present it a bit faster. The motivation and the problem is something similar to the work that we have presented already, but in this time we consider ordinary differential equations in terms of sensitivity of the parameters based on the model. Which parameter have a more strong and more weak, for example, I would say, effects on the model. The main question of the work is which model parameters must strongly derive malware spread, and where should defense be focused? I mean, which kind of parameters can control the propagation of the malware strongly and weakly? Okay, the model is the same of before, but this time with ordinary differential equation, just because for fractional and partial differential equation is kind of open problem here. And the contribution is computing R0, which is the main parameter, and I mean, which characteristics of the system, and sensitivity analysis with respect to normalized RCEF and global sensitivity analysis. And we have done a comparative analysis with the older models, and we compare our results with 2-3 other models to see the model works well or not. The related work in the research gap is something like the models that we have seen before, and most of them are based on ordinary differential equations. But in most of them, they solved the model, but they didn't investigate the sensitivity of the parameters related to the performance of the model. The model, as we have seen before, is this is the model, the ordinary differential equation model, and these are the parameters. We want to see which kind of these parameters, which parameters with between these parameters has most strong effect on the system in terms of propagation and in terms of defense. The system, as we have seen before, there are two kinds of equilibrium points, free and endemic, which is where malware, for free, when we have the system is free of malware and the system is stable, and for endemic, when the system is, the malware persists in the system. And also we compute basic reproduction number, because this one is the most important characteristics of the model, and we will investigate the sensitivity of other parameters based on the situation of R0. Normalized sensitivity index of R0 with respect to parameter gamma, it should be computed with this formula. A positive or negative index increasing gamma rises or lowers RCEF based on being positive or negative index. And we can see here the parameters index sign and note which kind have the positive, positive effect, and some of them have negative effect. RCEF is R0 is most sensitive to these three parameters: omega, gamma, and sigma. We can see here this kind of parameters, and we will see the charts that will show how this kind of parameters affect the model. I try to do it real fast. Stratified Monte Carlo sampling split each parameter range into n equal probability intervals. Sample each one without the replacement, covering the full range. And also we use this model to, after ranking inputs and outputs, measures the monotonic correlations between each parameter and the number of infected nodes controlling for the others. Positive PRCC, rising the parameter, increasing infections, negative, decreasing them. Unlike local sensitivity, PRCC explores the whole parameter space simultaneously. We use Adams Bashford model predictor for precise time domain solutions. Baseline parameters have fixed some kind of parameters which is based on. Only the sensitivity parameter under study is varied. I mean, we choose which, we try to find which kind of parameters affect the most, affect mostly the system, and we vary this kind of parameters, not others, to control how the variation of these parameters affect system. Here we can see, for example, in this situation, effect of variation of, we want to control and we want to see the effects of the most strong parameters on the system. Here we see the effect of omega on the system, and we choose a range of omega, for example, 0.01, 0.208, and other, precise numbers, to see how omega, omega variation affect the system. We can see higher omega, the infections peak appears earlier. I mean, the peak of the propagation, and lower, malware becomes less prevalent. So we can see when the amount of the omega is a little bit higher, that we goes and we can receive the peak of the propagation very earlier than when the amount of omega is less. Here is the same thing related to the parameter sigma, and we can see larger sigma lowers both infected and recover counts and brings the peak earlier. But failed nodes can still act as a spreader. So removal alone does not stop propagation. So also, this is one of the most important parameters in the system, that the variations should be controlled in terms of control the malware propagation in whole the system. And we can see here how it affects infected during the time, recovered during the time, and infected infected during the time. Infected based on recovered. These two are based on time, and these two is the kind of the relationship between infected and recovered based on time. Here we can see another important parameter gamma. We can see here increasing gamma sharply and quickly reduces malware occurrence and rises recovered nodes in less time. So we can see the most important parameter is gamma. To control gamma, we can control the propagation phenomena. And here we can see the rate of recovered node over time based on these three amount of omega, and here the relation between recovered and infected node based on these amounts of omega. And here is the global sensitivity PRCC results. We can see here the effect of this kind of parameters on the model. So correlation, positive correlation with the infected nodes with this kind of 5 parameters, and with this kind of 2 parameters we have negative correlation, which is strong related to omega and weak related to gamma. I said because gamma is important because it can reduce the effect of propagation, but the effect is less than omega, that it can be, increase the propagation effect in the whole system, under the whole system. And here is the, comparisons with other baseline methods. There was not a lot of models that are studied the sensitivity of the parameters under propagation phenomena. So we found these two models and we compared our model based on the time with these two models. And the situation, I mean, the results are something similar, but a little bit, I would say, improvement on the on the model, on how we can control the parameters to control whole system. And here is based on node density. Here is based on phi, and the last one was based on the R radius of the. Based on radius, communication radius of the any node. And here is node density, how many nodes we have in the system, I mean in the network. And here we compare our results, and it's something similar, but some kind of improvements in the system to control the malware propagation. As conclusion, local and global sensitivity analysis of the multi-malware, this model were investigated, but based on differential, ordinary differential equations. And we found these three parameters are the most influential parameters on the system. And comparative study shows, okay, fewer infected nodes than two existing models across radius and density settings. For future work, this work it should be presented before the work that I presented at first, but also we can investigate the sensitivity of the parameters based on the model that we have presented before as such a future work, and other type of future work that we can focus on. So that's it. I try to compact my presentation based on that work. So if it was not good, I'm so sorry. I had to do this. Thank you.
Any questions?
So this is your work now, no? What is here the future work is related to what you presented.
Okay, the future work. We improved the model, and we solved the model, and we proved two theorems related to fractional order model based on uniqueness and existence. Yeah, but the investigation of the sensitivity of the parameters, because there we have more parameters.
Yes, sure.
Yeah, it's open now.
It's still open.
Yeah. This is the
Thanks for such a presentation. I close the session here. Thank you for your interesting presentation, your presence. See you later in the breaks, and of course in the gala dinner. Also there. Thank you so much.
Thank you.
No one told me nothing, so
I will double check it. Okay. Okay, thank you. So see you later.
you have my
Yes.
oh, thank you so much.